Hello again. We are continuing to look at generalized single degree of freedom systems. Both now we are looking at equations of motion and free vibration. Okay? And let us just look back at the problem that we were doing in the last lecture, and that was with Z0 as the degree of freedom, okay, and of course with an assumed shape psi x. And towards the end of the lecture I was actually solving the problem with psi x is equal to cosine pi x upon 2L. This was the problem that we were solving, and of course it goes without saying that this is equal to 2L upon pi and here we get 2L upon pi. Sorry, we are differentiating it. So this is pi upon 2L. This is pi upon 2L, the whole squared cosine pi x upon 2L. And so with that, we saw that if you took the m star was equal to m bar into 0 upon L 1 minus cosine pi x upon 2L the whole squared, and we saw that this was equal to m bar L 3 by 2 upon 4 by pi, and this is equal to 0.227 m bar L. Okay, so we've already gone this. Now K star was equal to EI 0 to L. Now this is equal to pi upon 2L the whole squared cosine pi x upon 2L the whole squared dx. So if I take this this becomes pi fourth by 4 squared, so that is 16 EI, and L squared, L fourth, 0 to L cosine squared pi x dx, and this is equal to, we saw was that this was equal to, this term becomes L upon 2, we've already seen that. So this becomes pi fourth EI upon 32 L cubed, because this term is L by 2. This we've already seen from here, so I didn't want to do this. And of course, we saw that P star, which is equal to 0 to L P bar into 1 minus cosine pi x upon 2L dx, okay, 0 to L 1 minus cosine pi x upon 2L. This becomes equal to P bar L into 2L upon pi. So this becomes equal to 0.363 p bar L. Okay. So, that is what we get, and having that, now let me just put this together in one context, and that is, what do we get? We get, if I take xi x equal to x upon L, this becomes xi prime becomes nothing but 2x. So, xi prime becomes 2x upon L. So, this becomes 2 upon L squared, and xi prime into 1 minus cosine pi x by 2 L, xi double prime becomes equal to pi by 2 L the whole squared sine pi x upon 2 L, and for this the m star is equal to 0.2 m bar L, k star is equal to 4 ei by L, and p star is equal to 0.333 p bar L. For this, m star is equal to 0.227 m bar L, k star is equal to 3.05 ei upon L cubed, because we got pi fourth upon 32 ei upon L cubed. So, pi fourth upon 32 becomes this, and p star becomes equal to 0.363. So, now let us look at this particular values. I mean, you see what is the difference between this, and here we got omega equals to 20 ei upon m bar L fourth, and this omega turns out to be equal to 13.436 ei upon m bar L fourth. So, note this. So, let us look at this and let us look at this. Very, very interesting things that we see. If you look at this, this gives omega equal to 20 ei upon, forget the ei upon m bar, because ei upon m bar L fourth exists in both. In this case, this is 20, this is 13.436, okay. This is 0.2, this is 0.227, this is 4, this is 3, this is 0.33, 0.363. And why is there such a huge difference? Well, if you look at this, this assumes that the curvature is a constant, and curvature constant implies that it is a constant moment problem. Now, note that a constant moment is not a very accurate estimation, constant curvature, constant moment, because this is the problem, this is what the load is subjected to. Constant moment would mean that moment over here and here are going to be the same. In a cantilever, that you obviously know that is not the case. The moment is 0 at this end and is a certain value at this end. So, it cannot be constant. So, obviously, this, although it satisfies the geometric boundary condition, it violates the basic curvature and the moment relationship over here in this particular case. So, obviously, this is a forced, understand that when we force system to behave in a particular manner in which it is not supposed to, what happens is the k star goes up, because you are restraining, you are constraining the structure to deflect in a particular way. When you constrain it, your k star value goes up significantly. If the k star value goes up significantly, omega becomes much larger than it should be. Whereas, if you look at this particular one, if you look at this, this is the xi prime. let us put xi over here, xi x equal to L. If you put x equal to L, okay, you get what? You get sine pi by 2, so this becomes just this value. And if you put x equal to 0 over here, you get this equal to 0. So, curvature is 0 at one end. So, there is a variation of curvature, and since it incorporates the variation of curvature, you see k star, you look at the other values, m star only 10% variation, p star again only about 10% variation, k star almost 33% variation. This is 33% higher, and which is why if you look at this, this is almost root 20 would be about 4 point something, and this would be about 3 point something, almost 25% error in omega bar. Okay. So, therefore, this is closer to the real variation, and this is of course very constrained. Okay. I would leave it to do it with the other specific, the one that I have done, and you will see that in that particular case, if you take 3 x upon L squared, you will get that m star becomes about 0.226 m bar L, k star is going to be 3 ei by L cubed, and so therefore, the value of that omega is going to be about 13.4, very close to this particular value that you get. Okay, that is the beauty of this method. Okay. Now, the question then becomes is that, well, how do we get an appropriate xi x? Okay. Now, this method, the method that I am going to be talking about right now, is actually known as the Rayleigh-Ritz method. And the way this is done is that the xi x is found by putting a UDL on the system and finding out the deflected shape, and whatever is the Z0, okay, the Vx upon Z0 gives me xi x. This is of course done with in a static sense. Okay. So, in other words, given a particular, let us say that you have a UDL, a cantilever, you apply a UDL on it and find out the deflected shape under this UDL. Okay. This is a static problem. It is a static problem. You can find out V of x, U of x, and Ux upon Z0 is a first estimate of xi x. If you use this particular xi x, it is almost clear that it will satisfy not only the geometric boundary conditions, it will also establish the equilibrium boundary conditions for this UDL case. So, in other words, it does approximate the relationship, and you see what happens is that why does this give a reasonably close result? Because it satisfies both equilibrium and geometric boundary conditions. So, the xi that you get is much closer to the real xi that you will get under vibration. Okay. So, that is all there is to it in this particular case, and then once you get here, so this is the way to get xi x. Of course, the other approach that we have, which is a Ritz vector approach, you can use any xi that satisfies the geometric boundary conditions. A more appropriate xi is this one, where you actually apply a UDL on the structure that you have, and you find out the static displacement and divide that by the displacement at the end, because that is the degree of freedom, and that gives you your first order approximation of your xi x. Later on we will see that this procedure is going to be used in a multi-degree of freedom sense to actually iterate to the true xi x that you have for a particular system. Okay, so that much. So therefore, what we have now is we have looked at rigid body assemblages, which are, in a way they are true single degree of freedom systems. The only thing is that because you can't appropriately, there are many different ways of defining a single degree, the degree of freedom. So, we take that degree of freedom as any generalized displacement. For example, if you think back, I took rotation and I also took a displacement at a particular point, but they are related to each other. So, the rigid body assemblages that I looked at earlier were true single degree of freedom problem. Now, the last lecture and this lecture, what I am talking about are not true single degree of freedom systems. They are actually continuum systems, and we are making approximations, and the approximation that we are making is by assuming that the displaced shape under a specific, in a particular, at any instant of time is given by a shape function into the generalized displacement z0 of t. If you look at it mathematically, what we have actually done is we have taken this particular mathematically, physically what we have said, we have already talked about. Mathematically what we have done is we have taken u x of t and made it into xi x z0 of t, where this represents the shape function and this represents displacement field time history, and this is the generalized displacement time history. So, if you look at this mathematically, what have we done? We have taken a function which is a function of x and t, and we have separated them out into two functions, one a function of x and another function of t. So, this is known as separable functions, okay? And in this particular case we are assuming, note this is an assumption that the shape function is independent of time. The shape function is independent of time, and this is the generalized displacement time history. So that if you look at a situation where we look at curvature, this curvature is actually del squared u by del x squared of u. Okay. This is equal to, if I look at u double dot x of t acceleration, that is given by, so the time derivative and the spatial derivative are separated, okay, and that is the beauty of this approach. Note of course that xi x is an assumed shape function. However, if xi x is derived in the way that we have done, where we have said is that apply a UDL and find out the displaced shape and normalize that with respect to the degree, the displacement, you will get the shape function. If you use that xi x, you will get an estimation of k star, m star, p star and omega, which are fairly close to the real values. Of course, in real m star, k star and p star don't exist, but if you were to look at the solution, okay, for a particular p, and you will look at omega, which is the free vibration. So, you look at both free and forced vibration by taking this generalized single degree of freedom system with the xi x obtained through the Rayleigh-Ritz procedure, then by and large your solution both for free vibration and forced vibration are reasonably accurate. And note that what have we done? We have taken a very complex structure, made it into a generalized single degree of freedom, and the whatever response and free vibration response we get are fairly close to each other. How much better can you get? Okay. So, now let us look at solving using this and solving some problems in which, now you see, up till now we have looked at what? We have looked first at rigid bodily assemblage, and then I have looked at something which is a no rigid body, just a deformable body, where the deformation, only the flexural deformations are concerned, and we have solved that particular problem. Okay. So, now I am going to try to solve it using, let us look at a particular situation. And I am putting down this problem only as a specific kind of a problem. Okay. And let me put apart from that, I have E I, M bar, M bar 1, E I 1. This one of course is a rigid bar. This is a pin, and so this one I am saying is M bar 2. Let me look at this and call this as K. Okay. So, this is a problem. Now, if you look at this particular problem, okay, this has a flexible part and it has a rigid part, and there are some external. So, you see you have got this resistance and you have also got an external K. Now, how would I solve this particular problem? Well, let us look at this. Now, this is a problem that I need to look at very, very carefully, and what I will do is I will do the following. I will consider Z naught T. Okay, and let me put some load on it. So, let me put some PT. There is a concentrated load acting at this point. Okay. So, I will consider this as my generalized. Now, this is a generalized single degree of freedom, okay, because I have defined this as my. Now, how would I solve this problem? Well, again the question goes back to the same concept, and that is put Z0 equal to 1 and find out your displacement. So, let us look at this here is equal to 1. This is this way, this is fixed, and here you have continuity between the two. Okay. In other words, this is continuously connected, there is no pin here. If we do not have a pin here, then how does this go? This is a rigid bar. So, this rigid bar is going to go straight. Okay. Now, here note that this goes like this and comes like this. Okay. So, this then is my displacement pattern for unit, and if you look at this, this is my xi x. Okay. The xi x, now I can take it either way. I can consider these two separately. So, I can consider this as 1 and this as 2. Okay. For 2, I know my xi x. Since it is a rigid bar, my xi x is what? If I start my x from here, for 2, my xi x is equal to x upon L. It is obvious. It is, this is not an approximation. This is exact. Okay. So, if you look at it, if you look at your xi x for a rigid bar, the xi x is exact. For this, we need to get a xi x. Now, let me assume that I know this. This is not obvious. We will see later on. I am not right now solving this particular problem, but let us assume that, well, I can find out. How would I find out this xi x? Well, I would put a UDL on this one, okay, and under the UDL, this would also go up, and therefore, you would get all kinds of things. But here the point then becomes is that I know this xi x. I assume, or use the Rayleigh-Ritz approach to get this xi x. It's a known. This xi x is known. Okay. So, if I know this xi x, then what do I have? Let us look at what are the things that I have. Note that this is very interesting, because I can now write this as a problem which is of the following nature, and the nature is this, that note that this is going to have the problem m0 z plus k 0 is equal to p star. Now, to get this, all I need to do is write down, find out all the forces that are acting on this body, and based on that, derive the equations. Okay. So, and then use the virtual displacement pattern to solve the particular problem. So, if I do this, then I have the following. Okay, let me just draw this. So, what do? I give it z0, right? And if I give z0 over here, then what do I get? This one becomes xi x into z0, and that's xi 1 x, and here this is xi 2 x into z0, where xi 2 x I know is x upon L. This is exact. This is assumed. Okay. So, if I have these kind of loads, then now what are the things that I am going to have? I am going to have the following: this m star 2 giving rise to inertial forces. I am going to have this spring give rise to what? kz0 load. Okay, I am going to have this mass over here, mass undergoing inertial forces. In addition, I will have the moment over here also, flexural deformation occurring over here, and due to the flexural deformation, it will give rise to moments. Okay. So, those are all the forces that I have in the system. Okay. And what are those forces equal to? Well, let us look at this. In this particular case, I will take x from here to here. Okay, so this is the first part, and this I am going to take x. See, these are two different bodies. So, I am going to separating out the two bodies, and then since they are connected to each other, when you write down the virtual work equation, all of them will be connected to each other, right. So, if I put it this way, and this is xi 1 x, okay, corresponding to the mass, I will have m bar 1 into xi 1 dx. Okay, if you look at this, m bar into dx, m bar 1 dx is the mass per unit length, infinitesimal length, into xi 1 x into z naught is the displacement, and if I put acceleration, that will be the acceleration of this point. Okay, so that is this. Okay. What would be the moment at any particular point? The moment at any particular point would be EI, right? Then time x into z of t, because EI into this gives me the curvature, and EI into the curvature is the moment, is equal to the moment x of t. So, I have now figured out all the forces that this body is being subjected to. And if I look at all these forces, then let us look at what I get. I get the following. I am going to give it a virtual displacement. Again, virtual displacement, I am going to give del z0 as my virtual displacement. Note that this and this are going to be identical. This is going to be xi1 x into del 0. This is going to be xi2 x into del z0. Okay. And so, if I look at the work done by the internal and external forces, note that in terms of our internal forces over here, this is undergoing reverse. So, if I put all of them down, I will get what? I will get m2 m bar 2 dx into xi2 z naught double dot. This is the force multiplied by the displacement, which is equal to xi2 x del z, and this integrated from 0 to L2, which is 0 here, L2 here. Okay, that gives me the work done, and that's of course negative work done because it always opposes the movement. So, that is negative. That is external work. Okay. Then I have the K0. So, K0, so that is also going to do negative work, and that is equal to K0 into del 0, okay, because it is at that particular point itself, right. What else? Then I have minus m1 xi1 x dx z naught t multiplied by xi1 del z naught, okay, from 0 to L1, where this is 0, this is L1. Okay. So, these are the external forces, and on top of that I have the load, which the load is going to be, it is a concentrated load, and that is acting at mid span. So, that is going to be equal to half into del z naught. This is the work done by the load, half del z naught, because that is exactly at that particular point. Okay. And this is the external work done is equal to the internal work done. Internal work done is going to be equal to EI xi1 prime x zt, this is mx, and into, we have seen that is a virtual relative rotation, and that virtual relative rotation is given by xi1 double prime del z0 theta x, this is going from 0 to L1. So, if I put all of these terms and then know that del z0, which shows up in all of them, is arbitrary, then I can rewrite this equation in the following form, and that is going to be equal to, I am going to take all these minus terms on this side. So, this is going to look like this: 0 to L m1 xi1 squared x dx plus, sorry, 0 to L1, 0 to L2 m2 into xi2 squared dx into z double dot plus 0 to L1 EI xi1 whole squared into dx plus k into z0. So, these are z0 plus is equal to p into half and this L0 disappears. So, you see what is M star? M star is this, K star is this, and P star is this. So, you see ultimately if you really look at it, all that happens is that all you need to do is you need to now find out, you don't need to do anything. In M star, you find out whichever M mass per unit length, you multiply that by the corresponding shape function squared, and then all of them have to be added to each other. Then if you look at K star, one aspect is distributed flexibility. Distributed flexibility will have EI xi I double prime squared, and specific flexibility, which is specific springs. Those are given actually by K. Here it's 1 squared because it was K was applied at that particular point, but in a way it is K xi squared the way we've derived it. So you see the point then becomes the following, that if I have even a combination of structures, okay, then I have a situation where I do not have any specific issues associated with finding out M star, K star and P star. I will now solve a specific problem by using, without even going through first principles, and using this idea, I will solve a specific problem. Okay, let me take. So, this is a problem in which I have a mass, a point mass given by M1, okay, and I have a distributed mass over the entire bar. This is a flexible bar, okay. So, this is a flexible bar given its flexural rigidity is given by EI, okay. M bar is its mass per unit length and it is a constant, it is a uniform bar, okay, length L, and at the end I have and let me also put another, I will put it here. This mass is at L by 2, and I will put another, this is K1, I will put this as K2. Okay. Let us see what happens. And I am going to put it the following. I will put xi, so I am going to put that displacement, this is Z0, u x of t, where x is defined from here, u x of t is given by some xi x z naught t, okay, and xi x I am going to take it equal to, let us just take, I mean I know this is an upper, but let us just take this because this is a reasonably good. We know that it is a bad approximation, but for solution purpose let us right now take this as this. Okay. So, this is the problem, and let me try to get M star, K star and T star without going through the procedure of having to go from first principles. I am going to just derive them the way we have derived them. Okay. Now, M star, let us look at M star. There is a distributed part. The distributed part is going to be 0 to L M bar xi squared dx. That is the distributed part. We know that this goes. Plus there is one which is given over here, which is M1, which is going to be equal to xi at that particular L over 2 squared. Okay. You see, mass into whatever the acceleration at that point, so that is given by xi squared. Okay, I mean, again, I mean, one part xi gives you the acceleration, the other one gives you, you know, when you write down the principal virtual displacement, you get that. We've already gone through that. So that means this is my m star. Okay, what's my k star? And oh, by the way, I forgot to put a load, right? I'll put a load. I'll put the load over here. There is one load acting here, P1 of t, and there's another load acting here, P2 of t. So now let's go back. Okay, so k star. K star, there are two parts. One part is the distributed flexibility given by EI, and another one is these two concentrated. So if I do that, the distributed part becomes 0 to a EI xi double prime x squared dx. That's the distributed part in the k star, and then I have k1 into xi at L squared plus k2 at xi at L by 2 squared. Right? I mean, it's very simple. We've already derived this. So this is the k1 is at L and k2 is at L by 2. So that's all. Okay, that's k star. And what is p star? Well, p star, there are two concentrated loads. So concentrated loads are going to be p1 into xi1 at L by 2 plus p2 into xi at L. So that's all there is to it. This is m star k star, and now let us derive this with xi equal to x upon L whole squared. So if you put xi x upon L the whole squared, then what do we get? Let me put down first what do I get as my, so xi x turns out to be equal to x upon L squared. So xi double prime x is equal to 2 upon L, then xi at L upon 2, well, L upon 2, 1/2 the whole squared, it's 1/4, xi at L is equal to 1. Okay, so I've got all the parameters over here defined, okay, and we've already done this particular, you know, for a constant one we've got, what would we get? 0.2 m bar L, right? So m star, if I look at it, then m star turns out to be equal to m bar 0 to L x by L 4th L plus m1 into xi squared. So that was 1/4. So 1/4 squared. So this is equal to, we know, 0.2 m bar L plus m1 upon 16. So depending on what your m bar and L is, that's your m star. We have derived it because this is known, this is known, this is known. We can find out what m star is. Okay, I'll put down some values. Okay, let's put down some values. Okay, let me put m bar is equal to 20 kg per meter. Let's take L is equal to 10 meters, and let's take m1 is equal to 1000 kgs. So total mass of the bar is 200 kgs, and this point mass is 1000 kgs. So if I do this, m star is equal to 200 into 0.2, that's 40, plus 1000 upon 16. So that is equal to 62.5. So m star is equal to 102.5 kg. See, I have m bar L, I have 200 kgs there, and I have m1 which is 1000 kgs. I have almost 1200 kgs of total mass, but the participating mass in that particular is just 102.5 kg corresponding to the end one. So, that is what my m star comes out to be equal to. Then what is my k star going to be turning out to be equal to? If you look at it, is going to be equal to EI and then 0 to L 2 by L dx plus K1 into 1 squared plus K2 into 1/4 squared. So, therefore, this is equal to 4 EI upon L cubed plus K1 plus K2 by 16. So, this is my K star. Okay? And so, now my omega is going to be equal to K star upon m star into omega. And finally, what is my P star equal to? Well, I had two loads, and those two loads, if I look at them, they are equal to the following. Let me go back. I want to show you the specific problem that we had, that I had considered, and that is this particular problem, right. So, this was a particular problem. P1 was at the half point and P2 was at the second point. So, it becomes equal to P1 into 1/4 squared plus P2 into 1 squared. So, P1 upon 16 plus P2. That is my P star. These are absolutely elegant ways. So, therefore, if I give you any problem where it is a mixture of distributed mass, if it is distributed mass, then the mass per unit length into xi squared dx integrated over the length over which the distributed mass is provides the contribution of the distributed mass to m star. If I have fixed masses, point masses, then the position of that point into the displacement in the shape function squared gives me the contribution of that point mass to the m star. Now, if you look at k star, there are two paths. There are distributed flexibility. If you have distributed flexibility where the flexural rigidity is given by EI, then the distributed flexibility is going to be EI xi double prime squared dx 0 to L, where L is the length over which the distributed flexibility exists. If I have fixed flexibility, fixed springs, then it is the spring constant into the displacement at that particular point in the shape function squared. That is the contribution to k star. Okay. And how do I get P star? Well, if I have distributed loads, then and where the distributed load intensity is given by P bar x of t, then P star, the contribution of the distributed load, is going to be integration over the length over which the distributed load exists. Okay, P bar x of t into xi of x dx. That is the contribution of the distributed load. If there is a concentrated load, well, then it is going to be equal to P into the shape function value at that particular point squared. Okay, that is the contribution to P star. Suppose there was a moment applied. How would I do that? Well, moment into what? The work done is xi prime. So, it is moment, applied moment into xi prime at that particular point where the concentrated moment is applied. So, you see, this is the elegant way that we can work with generalized single degree of freedom and get m star, k star and p star. Okay. Earlier I looked at C star as for specific giving viscous dashpots, but we know that in real systems we never really compute C star. What we do is we assume, well, we compute, we measure say xi, where xi is equal to C star upon 2 m star omega, that is xi. So, all we do is define xi, so we do not really look at C star. So, we are looking at m star, k star and p star, and once you have that and you have the generalized degree of freedom, your equation of undamped equation of motion becomes m star z 0 double dot plus k star into z 0 plus p star, okay, which is a function of time, and this is all that we solve. This is a single degree of freedom problem, and when you solve that, you've got it. Okay. So, just to say that we have looked at true single degree of freedom and generalized single degree of freedom systems at this particular point. But of course, once you have the equation of motion of a single degree of freedom, then the solution process is what we have looked at for the last many lectures. Okay. So, I am done now with single degree of freedom system problems. From next time onwards, we shall start looking at multi degree of freedom system problems. Thank you very much. Bye bye.